So let us start from here. So we are calculating motion and we're talking about the average speed and the average velocity. So these are the two quantities that we talk about now. You should have a clear understanding of the difference between distance and displacement. So if you have a clear understanding what displacement is and what distance is, then you can understand certain other things like the average velocity and the what you call the instantaneous velocity and average speed. So all these things, the instantaneous and average speed, these two are again different quantities, and the instantaneous and average velocity, and what are the difference between all of them, we are going to understand that here. So let us say we calculate the average speed. So average speed is basically defined as so it is total distance over total time. Okay, so this is the average speed. So let us say if, for example, a car is traveling 50 kilo. A car is traveling 150 kilometers in 2 hours. Okay, so a car is traveling 150 kilometers in 2 hours and then travels 100 kilometers in 1.5 hours. So what is the average speed? So the total distance is what? 150 kilometers and 100 kilometers. So it is 150 kilometers per plus 100 kilometers, which is 250 kilometers. That is the total distance that it has traveled. So, and the total time it has taken is 2 hours plus 1.5 hours, which is 3.5 hours. So then we can calculate the average speed as the total distance divided by total time, which is 250 kilometers divided by 3.5 hours, which is 71.4 kilometers per hour. So it is basically the average speed of an object. It is moving faster earlier. So, and then later it is moving slower. And then in that case, it's the average speed of the two motion. The speed in the first half is different from the speed in the second half, but then we take the total distance it has traveled over the total time and divide it, the total distance by total time, then we get the average speed over the complete motion. So that is how we calculate the average speed. Now what is average velocity? So average velocity is basically total displacement divided by the total time. So that is the average velocity. It is not the total distance divided by total time. It is the total displacement divided by total time. So if an object is taking a circular lap and coming back to the same point from where he or she has started, then its displacement is zero. So its average velocity is zero. Whereas it is having some speed. Its average speed was there, which was finite, which was non-zero, but the average velocity would be zero because its displacement over the total period is zero. So whatever the time is final minus initial, but on the numerator you have zero, so then you can say the average velocity is zero. So again reconsider the same kind of a situation that we had earlier. So you have in the previous example, it was an east-west road and we defined east as positive. The car traveled 150 kilometers east, which is plus 150 kilometer, and then took around and traveled 100 kilometers west, so which is minus 100 kilometers. So the initial position was 0. The final position is 150 plus minus 100, which is 50 kilometers. Okay, so the displacement is simply x final minus x initial, which is 50 minus 0, which is 50. So that is the total displacement. And the total time is 3.5 hours. So basically average velocity is 50 divided by 3.5, which is equal to 14.3 kilometers per hour. So the average velocity is certainly very different from the average speed. The average speed that turned out was 71.4 kilometers per hour, whereas the average velocity turns out to be 14.3 kilometers per hour. So you can see there's a huge difference between average speed and average velocity, and that significant difference is basically how you define quantities in physics and what actually they mean. So average speed would tell you what is the total ground covered or how much was the activity. Whereas this average velocity is covered with the outcome. What was the total outcome? The object started somewhere and ended somewhere. So there was the total outcome was there. So the final displacement minus the initial displacement is taken, and then final position minus the initial position is taken as the displacement, and then the total outcome is divided by the total outcome of the time that it has taken, and then you divide the two to get the average velocity. So the difference is basically in terms of direction. The average speed is basically a scalar quantity and it does not depend upon the direction. Whereas average displacement, because average velocity is a vector quantity because the displacement itself is a vector quantity. So the displacement has a sign in one dimension, either it is positive or negative. So best thing is that when you divide that displacement by time, you will get the quantity which is either positive or negative. So the average velocity, which is average displacement over total time, would be a vector quantity because it has got a sign, either positive or negative. So either the velocity, the average velocity is in the positive direction or it is in the negative direction. So basically, they differ in the sense of direction. The average speed is a scalar quantity and average velocity is a vector quantity. Then we talk about the instantaneous velocity. So it is basically, as you can see here, let us say an object is moving with certain velocity v. Certain velocity, it is covering a certain distance actually. So it goes from here to here. So it has covered a distance x, okay, or delta x. The total displacement is delta x. And the time it has taken is delta t from this point to this point. So the object is moving from this point. So what would be the instantaneous velocity of that object? So velocity of that object at that instant of time. So velocity of an object is always definable at every instant of time. So it has covered a distance delta x in a time delta t. Then we define the instantaneous velocity as delta x divided by delta t. But now you have to be very careful. What we do is we have to take the limit that delta t is tending to 0. So you understand, we are talking about a very small fraction of time. What was the displacement in that small fraction of a time? And in that small fraction of a time, the displacement is delta x. Then we divide the displacement by time and then take the limit of the time taken to be tending to 0, almost instantaneous. So almost instantaneously, what is the change in the position divided by the change in the fractional or a very small change in time? That would be the instantaneous velocity. And that is basically also written as dx by dt. So it's the derivative of the position with respect to time. So dx by dt is basically delta x by delta t with limit delta t tending towards 0. So this is your introduction, the first introduction to derivatives. Dx by dt is the derivative of x with respect to time. So we will discuss all that later on in the different other chapters also, because this kind of definitions are very important there also. So we are talking about uniform motion. So a uniform motion is basically the simplest kind of motion we can talk of. So it's the object is moving with a uniform speed. Its speed is not moving. Also, its velocity is also not changing. So its direction is also not changing. So it's basically uniform motion in one dimension. The direction of the object's velocity is not changing with time, and the magnitude of the velocity is also not changing with time. So it's the simplest kind of motion, and in which the direction of the motion not changes, and the value of the velocity or the speed magnitude is also not changing. So the direct consequence of this is that in a uniform motion, the distance is always equal, distances are always covered in equal times. Okay? So basically it is like this, that if an object moves 1 meter in 1 second, and then in the next second also it is going to move 1 meter in the same direction. In the next second again 1 meter would be covered by that object in the same direction. So it's a uniform motion, its speed is not changing, velocity is also in the same direction. So it is basically the first and the simplest kind of motion. There is, in that case, the acceleration is zero. So either the direction is not changing or the magnitude is not changing. So the velocity's direction and magnitude are unchangeable. So in that case, the acceleration is zero. And so that is the simplest uniform motion in one dimension. So in a real world, we can talk of, for example, a car traveling on a long straight highway when it cruises control set to a constant speed. The cruise control of that car is set to a constant speed, and in that case, it is moving in a straight line with a constant speed. So that would be a uniform motion in one dimension. A rolling ball on the lane after it has been released again is a uniform motion in one dimension. Similarly, a train moving in a straight track or a hockey puck is gliding across a smooth flat sheet of ice. So these kind of things are uniform motion. So when we're talking about a uniform motion, now we come to the predictive power of physics. How the physics is going to predict the position of an object at a future time if we know the initial condition, and also we know the condition that the motion is uniform, and we know the magnitude of that velocity and the direction of that motion. In that case, we know certain initial conditions, and we require what are the basic criteria that define that system. Then we can predict what would be the position of that object at a later time. So we define velocity, as I've already said, as delta x by delta t, and that velocity is average velocity as well as instantaneous velocity in case of uniform 1D motion, because the direction of the velocity and the magnitude of velocity is not changing. So the instantaneous velocity of the object is also the average velocity. It is not changing. So that at particular instant, if an object is moving with a certain velocity, it's not changing with time. So its average velocity is also the same. So basically, v is delta x by delta t, simply stated, and v is a constant. So in that case, we can rearrange delta x is equal to v dot t. What we can take is, we can take delta t on the other side. We can take delta t on the other side, and then delta x would be v dot t. That is velocity times the time that it has taken. That would give you the total displacement. And then this displacement is actually nothing but del x final minus x initial. So then x final minus x initial is v dot t, and then we can say that the final position x final is x initial plus v dot t. So xf is equal to x naught plus vt. That you already know, that you know now from this. So basically, this is the simplest formula of predicting what would be the final velocity. If you know the initial velocity, if you know the initial position and the velocity and the time taken to cover that motion, then you know how much would be the final position of that object. So we can take some examples in this. So this demonstrates a fundamental pattern in science. If we know the initial state of a system, its initial position, and then we know the rules governing the evolution over time. The rules that are governing this system is that the velocity is constant. It's a uniform one-dimensional motion. So we know the rules that are governing the motion of that system. We know the initial position and the time taken for the process to complete, for the motion to complete. then we know what would be the position of that object at a future time. For example, here, let us say a cyclist is traveling at a constant velocity of 8 meters per second and starts at position x initial 2 meters. So its velocity is 8 meters per second. The cyclist is at an initial position of 2 meters. So her position at after 10 seconds can be predicted by this equation. That is, x final is 2 meters plus 8 meters per second, that is the velocity, times the time. So that is equal to 2 plus 80, which is equal to 82 meters. So we have found out what would be the final position of the cyclist after 10 seconds. So this is the first equation of motion in 1D motion. We can also draw a graph to understand this, which is called the position versus time graph. So a position time graph is basically, it is when you draw basically on the y-axis you plot the position, and on the x-axis you ascribe the time. So then you plot the position versus time graph, and the slope of that graph will give you delta x by delta t, which is the average, which is the velocity, either average or instantaneous. So for example, if I draw this here, I draw a position time graph here. So here, as I said, on the x-axis we are plotting time, on the y-axis we are plotting the distance as a function of time, or rather the displacement as a function of time, or the position. So x is the position of an object as a function of time. So let us say time is marked in seconds. So it is 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. Similarly, the position is marked in meters: 1, 2, 3, 4, 5, 6, 7, and so on. So it is in meters, and time is in seconds. And if the object is moving, so it is moving uniformly. So it is moving, it was 2 meters, let us say, at 1 second. It was 0 at 0 second, and it was at 0 position at 0 second. Then it was at 2 meters at 1 second. Then 4 meters at 2 seconds. Then at 3 seconds it was at 6 meters, and so on. So uniformly it is moving. So we draw a straight line. We join all the points, we get a straight line. So we know that at 1 second its position was 2 meters, at 2 seconds its position was 4 meters, and at 3 seconds its position was 6 meters, and so on. So from here, from this graph, you would know what is the slope, what would be the slope of this graph. It's a straight line graph which represents uniform motion, and in that uniform motion, the slope of the graph, which is equal to delta x by delta t, that would give you the velocity of that object. So let us say we take delta x here, from here to here. So the delta x is from here to here, which is equal to 6 minus 2, which is equal to 4 meters, and delta t for the same delta x is 3 minus 1, which is equal to 2 seconds. So then the velocity, the slope would be delta x by delta t, which would be equal to 4 divided by 2, which will be equal to 2, and the units would be meters per second, because t is in seconds and x is in meters, so the unit is meters per second. So the velocity of this one dimensional uniform motion, which is represented by this graph, is basically delta x by delta t, which is the velocity, and this is equal to 2 meters per second for this graph. Now let us say we can talk about different cases. So there can be different cases that we can talk about. Like for example, if the object is at rest. And so let me draw it here. So if an object is at rest, so you have time here and x here. So object is at, let's say x is equal to 2 for all time. So basically it remains at 2. So basically it is a horizontal line for all time which is moving in this direction, the forward direction, time is moving, but the object's position is not changing. It is 2 at time t is equal to 0, and it is also 2 at a future time, let us say 5 seconds. So this would be at rest. Similarly, for another object which is moving with a uniform velocity in the east direction or in the forward direction, we would have a positive slope, time versus x. So it is positive velocity. And if the object is moving with a negative velocity, then its slope would be negative. So in that case, it is moving in the opposite or the negative direction, and that is negative velocity. So you can see that different cases for a uniform motion, either at rest or with a positive velocity which is having a positive slope, or negative velocity with a negative slope. Similarly, we can talk of velocity time graph. So velocity time graph is also there, and again there are three cases. For, let us say, zero velocity, which would be a horizontal line, that means the object is not moving, its velocity is zero, and a horizontal line below the time axis in the negative direction would mean a velocity would be consistently negative, and a horizontal line on above the time axis represent an object which is consistently positive, which is having a velocity which is consistently positive. Okay. Second thing is, let us talk about the two things. So here you have, let us say, a position time graph is there, and I've already told you in the position time graph, the slope of the graph tells you the velocity of the graph. Now in the case of velocity time graph, so if it is horizontal, that means it is not moving, the velocity is zero. Or rather, if it is not zero, it is, let us say, it is having a constant value. So it is a horizontal basically, because the velocity time graph would tell you that the velocity is constant. Okay, and the, let us say, if the velocity time graph is like this, then in that case it has got a constant acceleration. The velocity is changing continuously and constantly with respect to time. So the change in velocity is constant, and so it has got a uniform constant acceleration. And if the velocity is, and if velocity time graph is negative, like this here, below the time axis, then that means the velocity is negative. ठीक है ना? So these are the different, you can say, different uh, the different conditions that you can have. Now the velocity time graph in which the velocity is constant would tell you a uniform velocity one dimensional motion, and in which the velocity is positive. And if it is negative, in the negative direction, that in that case the velocity graph would be below the time axis. And then, very importantly, let us say if a velocity is 5 meter per second here, and let us say here it is minus 2 meter per second. Okay, then it is 5 meters per second here, and then it has covered a certain distance with this velocity. So its velocity is 5 meters per second, and it has moved a certain distance from t1, let us say at 1 second, to t2 at 5 seconds. So what we do is we take the area below this curve between 5 and 1. So what is that area going to represent? This area. So the area would be basically height times the width, as you know. So the height of this parallelogram is 5, as I've marked on the y-axis, and on the other x-axis the distance covered or that width is 5 minus 1, which is 4. So the area under the curve is 5 times 4, which is equal to 20, isn't it? This distance or this displacement in time is 5 minus 1 seconds, which is equal to 4 seconds. And this displacement in velocity is basically from 0 to 5. So basically it is 5 meters per second. So basically you multiply 5 by 4, what you are getting is 20. And actually you are multiplying velocity with time. So this is equal to delta x, as I have told you earlier. So the area under this curve will give you the net displacement. So this is basically what a velocity time graph is going to tell you. So you understand what is distance time, position time graph telling you. The position time graph is telling you the velocity of the object. The slope of that graph is going to tell you the velocity of that object, and the velocity time graph is going to tell you the displacement. Okay, so this is all these two graphs are complementary to each other. One graph tells you the velocity, the position time graph tells you the velocity, and the velocity time graph tells you the displacement or the change in the position, the net change in the position. So this complementary nature of the two graphs you will understand later when we do about calculus, when we learn about integral calculus and differential calculus. So basically this is the integral calculus. Here you are actually integrating the velocity with respect to time. So that is an area that it has covered. So it's a part of integral calculus. Calculus when we are calculating areas, and that part, as I've already told you about the velocity, which is basically the slope of the graph, that is dx by dt, which gives you the velocity, and that is differential calculus. So the calculating slopes mean you are differentiating, and calculating areas mean that you are integrating. So you will learn about them in detail. This is your first encounter, and you should remember a velocity time graph complements a position time graph. One tells you the other. From one you can get the information of the other. Okay? So I hope you have understood this. So let us talk about certain applications and practices that we require. So you can go through this whenever you're doing a problem in physics. You should follow these points carefully. First of all, you should read and visualize carefully. Read the problem to understand the scenario. Draw a simple diagram. Label the start and the end points. Then establish a framework. Define a frame of reference by choosing an origin and positive direction. So always reference frame has to be defined. Then list knowns and unknowns. What are the knowns? For example, initial position, final position, time, velocity, etc. These are the knowns. Then the right tools you have to find out what formula you are going to use. In this case, the formula that we have actually used are the three formulas that we have defined. One is the formula for average velocity, which is also equal to the instantaneous velocity, and also what is the speed, and then also what is the final velocity in terms of initial velocity and velocity, the final position in terms of initial position and the velocity and time. So x final is equal to x initial plus vt. So you have to clearly think what formula you are going to use when you are tackling a certain problem. Then you should know the units. So every equation should be expressed in the same units. The right hand side of the equation should be expressed in the same units as the left hand side of the equation. So if the two quantities are given in different units, then you have to convert the units first before plugging them into the equation and solving to get the final answer. Okay, then signs have to be considered. So if there is a negative sign and you are adding two quantities, actually one quantity added with a negative quantity, a positive quantity added with a negative quantity is actually subtracting that quantity from the first quantity. So you have to take care of the signs. So these kind of things you have to, and then you should know what the interpretation is, how you can graphically visualize it, and from there you can derive, extract answers for your problem. So worked example, some simple examples. Like for example, a train is traveling at a constant speed of 72 kilometers per hour. So the speed of the train is simply 72 kilometers per hour. So 72 kilometers per hour is the speed of the train. In 90 seconds, how much distance it has traveled? That is the question. So the velocity is known to be 72 kilometers per hour and the time it has taken to cover the distance is 90 seconds. So this is the velocity and this is the time. We want to know how much displacement it has undergone. What is the total distance, unknown distance? Because it is one dimensional problem and the object is moving in a one direction only. So the distance is going to be the same as the displacement. Okay, so in that case, first of all, you convert the velocity is 72 kilometers divided by 1 hour. Then you convert the kilometers into meters. As I've told you in the previous lecture how to convert it, unit 1 over unit 2, u1 over unit 2. So kilometer is 1000 meters divided by 1 kilometer. Similarly, hours is 1 hour divided by 360, 3600 seconds, 3600 seconds. So then you have this formula. So you calculate velocity like 72000 divided by 3600. That is what you get, which is equal to 20 meters per second. Okay. So now you have found out the velocity which was given to you to be 72 kilometers per hour, but now you have converted it into meters per second. Okay. So you have changed the units. Now to calculate the displacement, you just take delta x, which is equal to velocity by time. So 20 meters per second into 90 seconds will give you 1800 meters. So simply stated, the time train travels 1800 meters in that much amount of time. 90 seconds it travels 1800 meters second. Then something about, you can say, scalar and vector quantities. So let us say the same problem we are talking about now. A student walks 50 meters east in 30 seconds and turns around and walks 20 meters west in 15 seconds. So basically what is happening is a student is okay. So basically you have a student here which is moving 50 meters east, then turns around and walks 20 meters for the entire 45-second trip. Okay, so the total time taken for the entire trip is 45 seconds. So what is the total distance traveled? What is the total displacement, average speed and average velocity? These are the things that you need to calculate. So how will you calculate it? Simply, what is the total distance? That's the distance in the total path. So he has traveled 50 meters earlier and then 30 meters, 20 meters later. Okay. Then in that case, the total distance is 50 plus 20, which is equal to 70 meters. But the total displacement is not 70. So he started from the origin, traveled 50 meters, and then traveled back 20 meters. So how much he has covered in terms of the position, the final position that he has. So the final position, so you know delta x, the displacement is 50 minus of 20. So it is x final minus x initial. Okay. So the initial position is 50 and the final position is 50 and the initial position is 20. So basically when you're subtracting them, 50 plus minus 20 will give you 30. So this distance here from this point to this point is 30 meters. So this is delta x. So this is delta x simply. So this is the distance displacement that it has covered. What about average speed? Average speed is total distance divided by total time. So the total distance, as we have already calculated, is 70, and the total time is basically the entire trip was 45 seconds. 70 divided by 45 is going to give you 1.56 meters per second. So that is the average speed. But what about the average velocity? The average velocity is total displacement divided by total time. Okay, and then it is 30 divided by 45, because 30 is the total displacement that we have calculated here, delta x. So the total displacement is 30 meters. So basically it is 30 divided by 45, so it is plus 0.65 meters per second. So basically its average velocity is plus 0.65 meters per second in the east direction, because the sign is plus. So it means that it is in the positive or the east direction. So you can see the average speed is 1.56 meters per second, but the average velocity is 0.67 meters per second. So now let us draw a graph, okay, and then do a problem. So let us say a graph is given to you, a graph is displayed. Let us say I draw a graph here, okay. So basically we have a position, let us say we have a position time graph which is described here. So time versus position, okay. So there are three segments of a graph. A line from 0 meters from here at 0 second and 0 meters. The time is 0 second and the position is 0 meters. So this is 0, 0, the origin of the coordinate. It moves uniformly to at 4 seconds up to 8 meters. So at 4 seconds it has come to 8 meters. So this is the point which is 4, 8. Then a horizontal line from 4 seconds to 8 meters. So then it stops at 8 meters. So there is a horizontal line, okay, up to 7 seconds. Okay. So it moves from here to here like this. Then there is a horizontal line. So it is just staying at this point at 8 meters. So the new position or the new coordinates are 7, 8. And then from here, from 7, 8, it goes to 9, 4. Okay, so at 9 seconds, it comes back to 4. Okay, so this is the graph that you have. Starting from 0, 0, first it comes to 8 meters in 4 seconds, then it stays at 8 meters up till 7 seconds, and then comes to uh, uh, 4 meters here at 9 seconds. So that position is 4, 9. Okay. So this is the graph that you have. which is describing this problem. Now he is asking, you have to find out the what are the various quantities like the velocity, average velocity, etc. Okay. So from 0 to 4 seconds, the graph is a straight line with a positive slope. So from 0 to 4, the graph is a straight line with a positive slope. So what is the velocity? It is delta x by delta t. So it is equal to 8 minus 0, which is the total displacement over total time, divided by 8 minus 0 divided by 4, which is equal to 2 meters per second. Then in this segment from 4,8 to 7,8, the graph is horizontal. That means it is not changing its position. So its velocity has to be 0 because the position remains the same. From 8 meter it goes to 8 meter. From 8 meter it goes to 8 meter only. The position is always the same here. Okay. So in that case, velocity at this segment is 0. Then from segment 3, the graph is a straight line with a negative slope. So in that case, the velocity is delta x by delta t, which is equal to 4, which is equal to 4, which is the final position. Okay, oh, let me just rub it. I have what is this? Okay, let me undo it. So here it is actually, let me just see how to rub it. Yeah, ठीक है. It is on this. This is okay. It is now again here. So I'm getting accustomed to all this functions of this board. So it is actually 994. It is like this. So I had reversed the coordinates. The x coordinate or the time coordinate comes first, and the y coordinate or the position coordinate comes later on. So it is 94 here now. So let us talk about segment 3, which is this segment. Okay, this segment. So the position of the object has changed from 8 to 4. So the position has changed 4 meters, which is the final position, minus 8 meter, which is equal to minus 4 meters. And the time it has taken is 9 minus 7, which is the final time minus initial time, which is 9 minus 7, which is 2 seconds. So minus 4 by 2 gives you minus 2 meters per second. So that is the velocity of the cat according to this graph in the third segment. Okay, so we have calculated the velocity of each one of the segments here. Of 3 different segments by graphically, we are able to understand what was the nature of the motion of this particular object, which is a cat right now, and how it moved. Okay. So let us conclude here. So we can conclude that the study of one-dimensional motion, when you are confining it to constant velocity in a single direction, again it provides a comprehensive introduction to the foundations, principles of kinematics. Okay, the journey begins by establishing a precise language. Motion is relative and must be described with a defining frame of reference with a specific origin. This framework allows for unambiguous definition of an object's position. Okay. Building upon this language, the critical distinction between scalar and vector quantities is introduced. This distinction clarifies the difference between distance, that is the total path traveled, and displacement, which is the net change in position, as well as between speed and velocity. These distinctions are not merely semantic, they are representing different physical concepts that answer different questions about the object's journey. The analysis of uniform motion, either constant velocity, serves as an ideal starting point for quantitative analysis. It is governed by a simple yet powerful predictive model This is the predictive model. X final is equal to x initial plus vt, the first equation of motion, uniform motion in one dimension. So this is the first encounter with the predictive model here. And then graphical analysis is also very helpful in calculating and in finding out the various quantities. Like for example, slope of the position time graph reveals velocity, and the area under a velocity time graph reveals displacement. So these visual tools provide an intuitive understanding that complements and reinforces the algebraic equation, offering a glimpse into the more advanced relationships between position and velocity. By mastering these core concepts, students build the essential foundation needed to describe, analyze, and predict the motion of the world around us.